A resistor is a passive two-terminal electrical component that implements electrical resistance as a circuit element. Resistors act to reduce current flow, and, at the same time, act to lower voltage levels within circuits. In electronic circuits, resistors are used to limit current flow, to adjust signal levels, bias active elements, and terminate transmission lines among other uses. High-power resistors, that can dissipate many watts of electrical power as heat, may be used as part of motor controls, in power distribution systems, or as test loads for generators. Fixed resistors have resistances that only change slightly with temperature, time, or operating voltage. Variable resistors can be used to adjust circuit elements, or as sensing devices for heat, light, humidity, force, or chemical activity. Resistors are common elements of electrical networks and electronic circuits and are ubiquitous in electronic equipment. Practical resistors as discrete components can be composed of various compounds and forms. Resistors are also implemented within integrated circuits. The electrical function of a resistor is specified by its resistance. Common commercial resistors are manufactured over a range of more than 9 orders of magnitude. The nominal value of the resistance will fall within a manufacturing tolerance. Electronic symbols and notation. Two typical schematic diagram symbols are as follows: resistor, rheostat, and potentiometer, i.e. resistor symbol. The notation to state a resistor's value in a circuit diagram varies. The European notation BS 1852 avoids using a decimal separator, and replaces the decimal separator with the SI prefix symbol for the particular value. For example, 8K2 in a circuit diagram indicates a resistor value of 8.2 kΩ. Additional zeros imply tighter tolerance, for example, 15 mO, when the value can be expressed without the need for an SI prefix, and R is used instead of the decimal separator. For example, 1R2 indicates 1.2 ohms, and 18R indicates 18 ohms. The use of a SI prefix symbol or the letter R circumvents the problem that decimal separators tend to disappear when photocopying a printed circuit diagram. Theory of operation. Ohm's law. The behavior of an ideal resistor is dictated by the relationship specified by Ohm's law. Ohm's law states that the voltage across a resistor is proportional to the current, where the constant of proportionality is the resistance. For example, if a 300 ohm resistor is attached across the terminals of a 12-volt battery, then a current of 12/300 equals 0.04 amperes flows through that resistor. Practical resistors also have some inductance and capacitance which will also affect the relation between voltage and current in alternating current circuits. The ohm is the SI unit of electrical resistance, named after Georg Simon Ohm. An ohm is equivalent to a volt per ampere. Since resistors are specified and manufactured over a very large range of values, the derived units of milliohm, kiloohm, and megohm are also in common usage. Series and parallel resistors. The total resistance of resistors connected in series is the sum of their individual resistance values. The total resistance of resistors connected in parallel is the reciprocal of the sum of the reciprocals of the individual resistors. So, for example, a 10 ohm resistor connected in parallel with a 5 ohm resistor and a 15 ohm resistor will produce the inverse of 1/10 plus 1/5 plus 1/15 ohms of resistance, or 1 equals 2.725 ohms. A resistor network that is a combination of parallel and series connections can be broken up into smaller parts that are either one or the other. Some complex networks of resistors cannot be resolved in this manner, requiring more sophisticated circuit analysis. Generally, the Y-delta transform, or matrix methods can be used to solve such problems. Power dissipation at any instant. The power P consumed by a resistor of resistance R is calculated as, where V is the voltage across the resistor and I is the current flowing through it. Using Ohm's law, the two other forms can be derived. This power is converted into heat which must be dissipated by the resistor's package before its temperature rises excessively. Resistors are rated according to their maximum power dissipation. Discrete resistors in solid-state electronic systems are typically rated as 1/10, 1/8, or 1/4 watt. They usually absorb much less than a watt of electrical power and require little attention to their power rating. Resistors required to dissipate substantial amounts of power, particularly used in power supplies, power conversion circuits, and power amplifiers, are generally referred to as power resistors. This designation is loosely applied to resistors with power ratings of 1 watt or greater. Power resistors are physically larger and may not use the preferred values, color codes, and external packages described below. If the average power dissipated by a resistor is more than its power rating, damage to the resistor may occur, permanently altering its resistance. This is distinct from the reversible change in resistance due to its temperature coefficient when it warms. Excessive power dissipation may raise the temperature of the resistor to a point where it can burn the circuit board or adjacent components, or even cause a fire. There are flame-proof resistors that fail before they overheat dangerously. Since poor air circulation, high altitude, or high operating temperatures may occur, resistors may be specified with higher rated dissipation than will be experienced in service. All resistors have a maximum voltage rating. This may limit the power dissipation for higher resistance values. Non-ideal properties. Practical resistors have a series inductance and a small parallel capacitance. These specifications can be important in high-frequency applications. In a low-noise amplifier or preamp, the noise characteristics of a resistor may be an issue. The temperature coefficient of the resistance may also be of concern in some precision applications. The unwanted inductance, excess noise, and temperature coefficient are mainly dependent on the technology used in manufacturing the resistor. They are not normally specified individually for a particular family of resistors manufactured using a particular technology. A family of discrete resistors is also characterized according to its form factor, that is, the size of the device and the position of its leads, which is relevant in the practical manufacturing of circuits using them. Practical resistors are also specified as having a maximum power rating which must exceed the anticipated power dissipation of that resistor in a particular circuit. This is mainly of concern in power electronics applications. Resistors with higher power ratings are physically larger and may require heat sinks. In a high-voltage circuit, attention must sometimes be paid to the rated maximum working voltage of the resistor. While there is no minimum working voltage for a given resistor, failure to account for a resistor's maximum rating may cause the resistor to incinerate when current is run through it. Fixed resistor. Lead arrangements through hole components typically have leads leaving the body axially, that is, on a line parallel with the part's longest axis. Others have leads coming off their body radially instead. Other components may be SMT, while high-power resistors may have one of their leads designed into the heat sink. Carbon composition. Carbon composition resistors consist of a solid cylindrical resistive element with embedded wire leads or metal end caps to which the lead wires are attached. The body of the resistor is protected with paint or plastic. Early 20th century carbon composition resistors had uninsulated bodies. The lead wires were wrapped around the ends of the resistance element rod and so molded. The completed resistor was painted for color coding of its value. The resistive element is made from a mixture of finely ground carbon and an insulating material. A resin holds the mixture together. The resistance is determined by the ratio of the fill material to the carbon. Higher concentrations of carbon, a good conductor, result in lower resistance. Carbon composition resistors were commonly used in the 1960s and earlier, but are not so popular for general use now as other types have better specifications, such as tolerance, voltage dependence, and stress. Moreover, if internal moisture content is significant, soldering heat will create a non-reversible change in resistance value. Carbon composition resistors have poor stability with time and were consequently factory sorted to, at best, only 5% tolerance. These resistors, however, if never subjected to overvoltage nor overheating, were remarkably reliable considering the component's size. Carbon composition resistors are still available, but comparatively quite costly. Values range from fractions of an ohm to 22 megohms. Due to their high price, these resistors are no longer used in most applications. However, they are used in power supplies and welding controls. Carbon pile. A carbon pile resistor is made of a stack of carbon discs compressed between two metal contact plates. Adjusting the clamping pressure changes the resistance between the plates. These resistors are used when an adjustable load is required, for example in testing automotive batteries or radio transmitters. A carbon pile resistor can also be used as a speed control for small motors in household appliances with ratings up to a few hundred watts. A carbon pile resistor can be incorporated in automatic voltage regulators for generators, where the carbon pile controls the field current to maintain relatively constant voltage. The principle is also applied in the carbon microphone. Carbon film. A carbon film is deposited on an insulating substrate, and a helix is cut in it to create a long, narrow resistive path. Varying shapes, coupled with the resistivity of amorphous carbon, can provide a wide range of resistance values. Compared to carbon composition, they feature low noise, because of the precise distribution of the pure graphite without binding. Carbon film resistors feature a power rating range of 0.125 W to 5 W at 70 degrees Celsius. Resistances available range from 1 ohm to 10 megohm. The carbon film resistor has an operating temperature range of -55 degrees Celsius to 155 degrees Celsius. It has 200 to 600 volts maximum working voltage range. Special carbon film resistors are used in applications requiring high pulse stability. Printed carbon resistor. Carbon composition resistors can be printed directly onto printed circuit board substrates as part of the PCB manufacturing process. Although this technique is more common on hybrid PCB modules, it can also be used on standard fiberglass PCBs. Tolerances are typically quite large, and can be in the order of 30%. A typical application would be non-critical pull-up resistors. Thick and thin film. Thick film resistors became popular during the 1970s, and most SMD resistors today are of this type. The resistive element of thick films is 1,000 times thicker than thin films, but the principal difference is how the film is applied to the cylinder or the surface. Thin film resistors are made by sputtering the resistive material onto an insulating substrate. The film is then etched in a similar manner to the old process for making printed circuit boards, that is, the surface is coated with a photosensitive material, then covered by a pattern film, irradiated with ultraviolet light, and then the exposed photosensitive coating is developed, and underlying thin film is etched away. Thick film resistors are manufactured using screen and stencil printing processes. Because the time during which the sputtering is performed can be controlled, the thickness of the thin film can be accurately controlled. The type of material is also usually different, consisting of one or more ceramic conductors such as tantalum nitride, ruthenium oxide, lead oxide, bismuth ruthenate, nickel chromium, or bismuth iridate. The resistance of both thin and thick film resistors after manufacture is not highly accurate. They are usually trimmed to an accurate value by abrasive or laser trimming. Thin film resistors are usually specified with tolerances of 0.1, 0.2, 0.5, or 1%, and with temperature coefficients of 5 to 25 ppmK. They also have much lower noise levels, on the level of 10 to 100 times less than thick film resistors. Thick film resistors may use the same conductive ceramics, but they are mixed with sintered glass and a carrier liquid so that the composite can be screen printed. This composite of glass and conductive ceramic material is then fused in an oven at about 850 degrees Celsius. Thick film resistors, when first manufactured, had tolerances of 5%, but standard tolerances have improved to 2% or 1% in the last few decades. Temperature coefficients of thick film resistors are high, typically plus or minus 200 or plus or minus 250 ppm K. A 40 Kelvin temperature change can change the resistance by 1%. Thin film resistors are usually far more expensive than thick film resistors. For example, SMD thin film resistors, with 0.5% tolerances, and with 25 ppm K temperature coefficients, when bought in full-size real quantities, are about twice the cost of 1%, 250 ppm K thick film resistors. Metal film. A common type of axial leaded resistor today is the metal film resistor. Metal electrode leadless face resistors often use the same technology, and are also cylindrically shaped but are designed for surface mounting. Note that other types of resistors are also available in MELF packages. Metal film resistors are usually coated with nickel chromium, but might be coated with any of the CERMET materials listed above for thin film resistors. Unlike thin film resistors, the material may be applied using different techniques than sputtering. Also, unlike thin film resistors, the resistance value is determined by cutting a helix through the coating rather than by etching. The result is a reasonable tolerance and a temperature coefficient that is generally between 50 and 100 ppm K. Metal film resistors possess good noise characteristics and low nonlinearity due to a low voltage coefficient. Also beneficial are their tight tolerance, low temperature coefficient and long-term stability. Metal oxide film. Metal oxide film resistors are made of metal oxides, which results in a higher operating temperature and greater stability, reliability than metal film. They are used in applications with high endurance demands. Wire wound resistors are commonly made by winding a metal wire, usually nichrome, around a ceramic, plastic, or fiberglass core. The ends of the wire are soldered or welded to two caps or rings, attached to the ends of the core. The assembly is protected with a layer of paint, molded plastic, or an enamel coating baked at high temperature. These resistors are designed to withstand unusually high temperatures of up to 450 degrees Celsius. Wire leads. In low-power wire-wound resistors are usually between 0.6 and 0.8 mm in diameter and tinned for ease of soldering. For higher-power wire-wound resistors, either a ceramic outer case or an aluminum outer case on top of an insulating layer is used. If the outer case is ceramic, such resistors are sometimes described as cement resistors, though they do not actually contain any traditional cement. The aluminum case types are designed to be attached to a heat sink to dissipate the heat. The rated power is dependent on being used with a suitable heat sink. E.g., a 50W power rated resistor will overheat at a fraction of the power dissipation if not used with a heat sink. Large wire-wound resistors may be rated for 1000 watts or more. Because wire-wound resistors are coils, they have more undesirable inductance than other types of resistor. Although winding the wire in sections with alternately reversed direction can minimize inductance, other techniques employ bifilar winding, or a flat thin former. For the most demanding circuits, resistors with air-tin peri winding are used. Applications of wire-wound resistors are similar to those of composition resistors with the exception of the high frequency. The high-frequency response of wire-wound resistors is substantially worse than that of a composition resistor. Foil resistor. The primary resistance element of a foil resistor is a special alloy foil several micrometers thick. Since their introduction in the 1960s, foil resistors have had the best precision and stability of any resistor available. One of the important parameters influencing stability is the temperature coefficient of resistance. The TCR of foil resistors is extremely low, and has been further improved over the years. One range of ultra-precision foil resistors offers a TCR of 0.14 ppm degree C, tolerance plus or minus 0.005%, long-term stability 25 ppm, 50 ppm, stability under load 0.03%, thermal EMF 0.1 microvolts, degree C, noise minus 42 decibels, voltage coefficient 0.1 ppm V, inductance 0.08 microhenries, capacitance 0.5 picofarads. Ammeter shunts. An ammeter shunt is a special type of current sensing resistor, having 4 terminals and a value in milliohms or even microohms. Current measuring instruments, by themselves, can usually accept only limited currents. To measure high currents, the current passes through the shunt across which the voltage drop is measured and interpreted as current. A typical shunt consists of 2 solid metal blocks, sometimes brass, mounted on an insulating base. Between the blocks, and soldered or brazed to them, are 1 or more strips of low-temperature coefficient of resistance manganese alloy. Large bolts threaded into the blocks make the current connections, while much smaller screws provide voltmeter connections. Shunts are rated by full-scale current, and often have a voltage drop of 50 mV at rated current. Such meters are adapted to the shunt full current rating by using an appropriately marked dial face. No change need to be made to the other parts of the meter. Grid resistor in heavy-duty industrial high-current applications. A grid resistor is a large convection-cooled lattice of stamped metal alloy strips connected in rows between 2 electrodes. Such industrial-grade resistors can be as large as a refrigerator. Some designs can handle over 500 amperes of current, with a range of resistances extending lower than 0.04 ohms. They are used in applications such as dynamic braking and load banking for locomotives and trams, neutral grounding for industrial AC distribution, control loads for cranes and heavy equipment, load testing of generators and harmonic filtering for electric substations. The term grid resistor is sometimes used to describe a resistor of any type connected to the control grid of a vacuum tube. This is not a resistor technology, it is an electronic circuit topology. Special varieties: Cermet, phenolic, tantalum, water resistor.